Hi everyone, in this video I would like to show you how to fuse vertices in TopologicPy in order to clean up geometry that may have come from a different piece of software that was not very accurate in how it modeled the object that you are modeling. So basically this little example of the two cubes illustrates the problem. You could have both a kind of a gap as well as an overlap, as an intersection. So what I've done is I've taken one of the cubes, translated it or moved it to the side a little bit and rotated it a little bit so that it is not accurately kind of adjacent to the first cube. So how do we address this? How can we clean it? And obviously, like everything else, there are no perfect solutions all the time. There are some compromises that we need to make. And you will see at the end a caveat about this process. But to start with, if we take these two cubes and we, in TopologicPy, and this is by the way something that is available in version 0.4.93 or newer. So if you create a cell complex from these two cells, because they are overlapping, it actually will create three cells. So the little sliver or shard that you can see here is a kind of an artifact of this kind of overlap that you see here. And obviously all this kind of edge segmentation is because of the intersection that will happen somewhere around the middle here. So we get three cells, which is not ideal. That's not what we want. We wanted two clean cells. So how do we achieve this? So here is the possible solution, is to fuse the vertices within a tolerance. So this is made out of 4 steps. So the first step, and I'll go through them in detail, but let me just give you an overview. So the first step is to get the list of vertices of each cell and then make them into one long list, and to make a note of how many vertices are in each cell. So in this case, since they're both cubes, each cube will have 8 vertices, so it's very easy to re-extract them later on. Then you take this list of vertices of both objects, both cells, and then you fuse them within a tolerance. So you should know what kind of tolerance you are dealing with in order to get those vertices to fuse into one vertex. So there is a method called vertex.fuse, which I will go over in the next set of slides. Then after they have been fused, and then a list is returned to you, and the list that's returned is exactly the same length as the input list, but now the coordinates of the vertices in that list have been fused, so they are exactly have the same numbers in them. You re-extract the fused vertices of the cell that you wish to modify. So for example, if you want to modify the vertices of the second cube, you would extract from index 8 forward to the end of the list, because that's where those vertices were stored. And then you use another method called topology.replace vertices to replace the vertices of the cell in question with the new fused vertices. So basically it will take an object, it will take its list of vertices and the new list of vertices, and it will do the work of replacing the old vertices with the new ones. So let's go through this in some detail. So as I said, the first step is to get the list of vertices of each cell and concatenate them into one list, and you should make a note of how many vertices are in each cell. So vlist1 is topology.vertices of cube 1 or C1. vlist2 is equal to topology.vertices of cube 2 or C2. And then vlist, which is the total concatenated list, is vlist1 plus vlist2. Then you fuse the list of vertices within a tolerance. So the fused list now, this new variable, is equal to vertex.fuse, and you give it vlist, which we created before, and you give it a tolerance. In this case, I'm using 0.04. Obviously, you have to take a look at your data and decide what is the appropriate tolerance to use. So now we re-extract the fused vertices of the cell that you wish to modify, and in this case, we're going to modify the second cell. We're going to leave the first cell exactly as it is. So we're going to get a new list, which is the fused list, and this is kind of a bit of a Python syntax. That means from index 8 all the way to the end of the list. So we're getting the last part or the last half of the fused list. So this is what we will get. So this is the original. What you're seeing here is C2 in its original shape, the cube, and then the black dots are the new fuse list. And what you will notice is that only the ones that are on the side of the adjacent face, the middle face, are the ones that have changed because they got fused to the old or to C1. That is, if you can imagine it on this side. But these 4 vertices on the far end did not need to be replaced. So that is how it kind of works. I hope this is clear. So now we use topology.replace vertices to replace the vertices of the cell in question with the new fused vertices. So this is the call for it. So we're creating a new object called C2B, which is equal to topology.replace vertices. We give it C2, which is the original object. Vertices A is vlist2. So vlist2 was, if you remember earlier on, were the vertices of C2. So this is vertices A, replace it with vertices B, which is the new list. So it takes all the vertices here, puts them into here, and recreates a new object for you. And that is called C2B. Just one little note here that C2 is a cell, but sometimes C2B might become a cluster. So you might want to add a topology.self-merge C2B so that it converts it back into a cell. So if you don't get the same object type, make sure you self-merge and it should recreate the cell that you had before. So if we show now the new cell, this is C1 on the left side and this is C2B on the right side. You'll notice that the vertices are now perfectly aligned, and therefore we can create a cell complex out of these. So now creating a cell complex from 2 cells creates 2 cells rather than 3 cells. So this is the code for it. As you notice here on line 3, C2B is equal to topology.self-merge C2B to ensure that C2B is a cell. And then I create another cell complex by cells. I give it C1, but also now I give it C2B, and that creates a new cell complex. And when I get the cells of this cell complex and I list them, I get only 2 cells as expected. So the caveat is that there's no guarantee that the faces are orthogonal. Obviously we've changed them, and this is why the objects are triangulated first, because you might get distorted faces if you are just simply moving vertices. So you have to make sure that you triangulate first, and you have to test whether moving away from kind of an orthogonal face or 90 degrees causes any issues for your project. So just keep in mind that that will happen. This is a way to clean up and create cell complexes, but it cannot really ensure that everything is still orthogonal. I hope you enjoyed this video, and I will see you in the next one. Thank you.